Hi, I'm Nathanael.
And I'm Nick. We're Group 3B, and this is Lab 2.
For this part of the lab, we set up the laser and the microscope as before. And what we did is we mounted a knife on the rail and used the microscope to image the knife edge so we can make sure that the knife's on the rail. Then we put in a photodiode and we moved the knife blade across the laser beam, taking measurements at two different knife positions. We then put in a lens which let us image the inside part of the laser cavity, which we can't actually get to physically. And we did the same thing, taking measurements, moving the knife across in two different positions behind the lens. Okay, so for the first part of the lab, what we're trying to do is measure the beam waist of the laser. The problem is that the beam waist is actually inside the laser and therefore inaccessible. So what we have to do is we have to measure two widths of the beam outside of the laser, and in this particular setup they're on the same side. And what we do is we put a knife edge at a certain spot, put the knife through the laser, blocking off parts of the beam as we go to get a good profile of the beam, move the knife distance delta Z away, and then do the same thing here. And from there we can count, from having delta Z and both W's, we can calculate what the beam waist is.
Measuring the beam profile, we were able to calculate that at 84% the knife edge position and at 16% the knife edge position, while these two measurements in between would give us W1, which happens to be 0.705 millimeters. Moving the knife edge forward and recording its new position for delta Z, we needed to measure W2, which we did so by measuring the beam profile at 84% and 16% for the knife edge positions and calculating the difference to be W2.
The second part of the lab, what we did is we used the lens to image what's going on inside the laser. So we have a new beam waist here, which isn't quite the same as the actual beam waist. What happens is the lens Fourier transform what's going on inside the laser to over here. And because Fourier transform of a Gaussian is a scaled Gaussian, the new beam waist is just a scaled of the old beam waist that we calculated earlier. So for this setup, W1 and W2 are actually on opposite ends, so we have to use the other formula for Z1. But we do the same thing as before to calculate what the beam waist is.
After calculating W1 and W2 from our graphs, we then needed to calculate the rest of the equations, Z1, Z2, Z0, and W0. We used the beam profiling algorithm, which uses a quadratic equation, and solving for the constants A, B, and C, and plugging them into the quadratic equation, we were able to come up with two answers, one of which will be correct. We don't know this correct right now, but we'll plug them in and find out in a minute. We then took our highest value because we found that usually the higher value tends to be the more correct one, and we plugged that one in for Z0 and solved for Z1 and Z2. Now to verify that our Z0 is correct, we plug that into the Z2 minus Z1 is equal to the delta Z equation, and we're able to verify that it was approximately 400 millimeters is what we started with, so therefore the Z0 was equal to the 0.52998 meters. We then plugged that number into W0 equation, and we're able to come up with 327 microns, being W0. For the calculations with the lens, we then used the same equations as we did previously before, however, except for the fact that now that W0 is in the middle of our W1 and W2, we then use the equation for Z1 with a negative sign to the fact that it's on the opposite side. Z1 and Z2 into our delta Z equation, we find out that we are approximately 500 millimeters, which was what we started with. As we calculate W0, we find out that it is 172 micrometers, which is approximately half of the W0 that we started without the lens. After this lab, we found that by positioning the knife edge delta Z apart and measuring the locations of the knife edge, we were able to calculate W1 and W2 from the graphs, which we then used to calculate W0 from inside the cavity of the laser, which we would normally not be able to do. We also found out that we can move W0 out of the cavity and decrease its size by adding a positive lens at 2f.